It is now my pleasure to invite Michael Syracuse, partner of FXCollaborative Architects, and Cecil Scheib, Chief Sustainability Officer at NYU. They will be sharing their work on the largest passive house EnerPHit retrofit in the world, representing a type of project we will all need to excel at in order to meet our climate goals, increasing efficiency of our buildings and saving existing embodied carbon.
Hey everyone, good afternoon. I'm Cecil. How's everyone doing? We're going to mix it up, a little live presentation. I should say right away with folks from PHI, calling it the largest EnerPHit project in the world that's a hopeful word. It's not certified yet. Won't be for a while. The project's not built yet. We don't know who else might get certified in that time. So just take that as an aspirational statement, less than a factual one. And then I think we'll all be able to get along. Okay, so I'm going to talk a little bit about NYU and our carbon goals and this project. I'm going to take a little bit of like the 30,000-foot view, some of the economics, some of the things maybe that drive owners to do these things, and then turn it over to Michael for more of the details about the building, and it's, like embodied carbon. It's interesting because before I came to work at NYU, I founded an eco-village in the Midwest that focused on off-grid living and natural building. And we started in the 90s, and we are not aware of really passive house and ultra-low energy principles, but we did build out of local materials, including straw bales, press straw panels, like a wheat straw panel, local mud, local sand, poured clay floors, clay plaster, lime plasters. And I don't think I realized at that time how much we were really pioneering those carbon sequestering materials. And in fact, when I came to New York, part of it was, hey, I want to have a bigger impact. I want to focus on the operational carbon. We're not really changing anyone's mind by building, like straw bale homes in the country. And it's interesting to see that come full circle and the discussion come back around as we come down to the zero operational carbon buildings, back to the building materials. So maybe it's time for a trip back to Dancing Rabbit and see how they're doing at the Eco Village there. So NYU, you might have heard of it. We might surround the building we're in on 4 sides. I don't know. I can't say. I just work there. But we do have about 15 sites worldwide. We're one of the city's largest employers. We're one of the largest private universities in the U.S. 15 million square feet, more or less, in New York City, and Brooklyn, Manhattan. 1,800 separate utility accounts, so you can imagine our pleasure with things with local law 84, local law 87, local law 97. It's extremely simple and straightforward. But we have a big impact, right? We're like 1/3% of the city's emissions. So we have a chance. And NYU jumped into our climate pledges in the year 2007. When we helped found the what was then called the Mayor's Carbon Challenge, is now called the New York City Carbon Challenge, and we pledged to reduce our building emissions intensity 30% in 10 years. So again, we're like 0.3% of the city. So if we cut by 30%, that's like 0.1% of all New York City building emissions that we were able to reduce. So we said we do it in 10 years. We did it in 5. We were done by 2012. That was the equivalent of planting all of Manhattan and all of Brooklyn in trees in terms of the carbon sequestration using the EPA's calculator. Chris, you can probably tell me later how the EPA calculator doesn't get it quite right because it doesn't account for root mass. But in any case, we use the EPA calculator, and that's what we get. And at that point, we pledged a total 50% reduction in our operational carbon emissions by the year 2025. So in a couple of years, we'll be emitting just half of what we were when we started, and to be carbon neutral by 2040. again, this is all scope 1 and 2 on-site operational emissions, 99% plus of which are from buildings. And I do think, here in the city, I say NYU is 99% of our emissions from buildings. Citywide, we used to say, 75%. Now we're down to maybe 67, 70%. Nationally, maybe 45%. You see pie charts like the one we saw earlier, from Dr. Miner saying maybe 6%. But, of course, keep in mind all these categories are fuzzy, right? Because how do you allocate industry emissions, right? Some of industry emissions are for the products that are going into buildings. And some of like the electrical sector emissions, a lot of the electrical semester emissions are from energy going to serve buildings. So there's a lot of overlap in between those categories. And actually, one thing that's really fascinating is something at NYU that's being run out of the Tandon School of Engineering in Brooklyn called the Sustainable Engineering Initiative that looks at the fact. So, as Chris mentioned, like the main outputs of emissions in building materials are steel, aluminum, glass, plastic, and concrete. And we've talked a lot about concrete, and you'll hear more hopefully today, right, Amanda? You can talk about concrete? Yeah, okay, good. We can think about the recycled steel, the recycled aluminum, things like that. Plastic's a real hard one. And almost all of the energy used in making plastics out of fossil fuels comes from just 2 steps in its process where you put in tons of thermal heat. And so the folks over at Tandon are, how can we electrify the plastics making process? And when I say plastics, I mean all of the chemical feedstocks that go into everything, including all of these types of fossil fuel-based insulation. So if you're not going to use the natural insulations, the fossil fuel-based insulation, electrify those processes instead of using vast amounts of fossil heat. So this is going to sound very familiar to people in this room, have been talking about how to electrify the fossil fuel uses in our buildings for a decade or more. And it's exciting to know that people are working on the materials part of the process in the same ways. So let's all be fellow travelers on those things. We have one scope 3 goal, so off campus, and that's food. Food is about 1/3 of global emissions, and we have pledged to reduce it 25% by the year 2030. So as we go through this talk, right, it's about being intersectional. It's about looking at the whole picture, right? It's about looking at the building science that says that people think better, have better, cognitive function when we have buildings with cleaner air. We spend 90% of our lives indoors. It's incredibly determinative of our health. So fresh air, good light, views, toxics, low CO2, all these things are really important. That's why NYU is on the LEED standard. Everything we build or renovate is LEED certified. We have 2+ million square feet that's LEED certified or undergoing certification. But it is about the quality of life for our students and our faculty and really supporting the, like the academic enterprise. I think a good example of this is a student residence. This is a first-year dorm that we retrofit just about a decade ago. It's right down the street. It's right down the road on 10th Street, right at Broadway. So it was built as a hotel about 100 years ago. Heavy number 4 oil boilers in the basement, right? So not only tons of inefficient steam heat, but tons of particulates coming out and causing all the health problems, right, that heavy oil causes. And when we did that building renovation and we put natural gas fired condensing boilers on the roof. So we got them up out of the flood zone, right? If there's surface flooding, that now we've got them out of the basement. We don't have the particulates. This building is still fossil fueled because there's a little bit before we really started focus on going 100% electric, but it's actually, like electric ready because it's a low temp water loop in the buildings. And you could easily put in air source heat pumps in place of the condensing boilers on the roof. And that's all well and good, even including the fact that we added air conditioning. This is a building that did not have air conditioning in the year 2013. Thank you, freshmen. You just paid $50,000 to come to NYU, and you don't have AC. But now we've added AC, and even including that, cut its operational costs and its operational carbon in half, right? So that's like the dramatic nature of the renovation. I always tell NYU students, who come to us with climate knowledge, but also climate anxiety, climate despair. Can we act fast enough? Will we act fast enough? Yes, change is possible. Big changes are possible fast. And I also tell them the story that it's tempting to only focus on the carbon and the climate and the CO2 emissions, but let's talk about the fact that these old single pane windows in metal frames that didn't fully close meant that NYU students who live on 3rd Avenue, Broadway, 5th Avenue, 14th Street, downtown Brooklyn, right? Some of the loudest places in the city, and can't sleep, can't relax, can't study because it's so noisy. Give them a good window that closes and has that sound control. And we've all seen like the Passive House video, right, of the Brooklyn brownstone where the door gets closed and like the jackhammer noise goes to 0, right? Give them a quiet place. What if they do better on their midterms because they got a good night's sleep? What's the value of that? So let's let our story be. We live inside our buildings. Let's make our buildings better for ourselves, for our academic function, for our happiness. We'll let the energy savings help pay for it, and we'll be doing our part to help fight the climate crisis. Isn't that a better story than getting people scared about rising ocean levels? That's true too, and we have to talk about that. But is that what is really motivational for people when it comes time to make the decision about a building retrofit? So now I'm going to talk about Rubin, which is the topic of our talk today. So Rubin is very much like Brittany. It was also built more or less 100 years ago as a hotel. NYU has operated as a student dorm for about 50 years, since the late 60s, I guess a little more. And this time we have the chance to do everything we learned on Brittany and more. So this time we're going for 100% all electric retrofit, right? Let's add insulation from the inside. Let's do that air sealing. You'll hear more about this from Michael. Once we brought down the building loads, now let's go to air source heat pumps on the roof. Let's go to a water-to-water system in the basement for the domestic hot water. Let's add that internal ventilation. So we are ducting air to student units. We are doing retrofit ducting inside a 100-year-old building so that students can actually get delivered filtered air that has like the heat recovery to their room so they don't have to open that amazing triple pane Schuco window. So that I just happen to name Schuco. It's not because anyone from Schuco is here. I just want to point that out. I would have said Schuco regardless. But they can keep that window closed, right? Because what is the point of giving them, like a triple pane window if they're just going to open it, right? For a little bit of fresh air, right? You got to give them that fresh air. Much more resilient, right? Hopefully you've all seen the charts. What happens if there's a power outage and how a building with a good envelope that's air sealed and insulated will hold its temperature even without power. The building's very attractive, both NYSERDA and the utility, right? Everyone wants to see these high-performing retrofit projects come across the plate. We've all been talking about it for years. How many years have us true believers been coming to the Passive House projects? But the number of large retrofit projects in the building, in the city is a very short list, if any, right? But when I started poking around in city data, I think there might be 1 billion square feet of like steel frame, masonry or brick clad, this general vintage, like pre-war or shortly post-war construction in the New York City area that could benefit from this type of work, right? It's hugely, like influential. So we all want to see this get across this plate. And when people say, well, we're not really focused on the retrofit, we're really focused on, new build and things like that, it's just too hard. Is it? Like, let's talk about what we did. Let's talk about how much it costs. Let's talk about the engineering challenges. Let's talk about how we're going to get there. We face so many challenges on this project, right? It's in a historic district, it's historic building. So what you could put on the roof in terms of sight lines, you can't change the facade. There's so many restrictions. We have a couple benefits as NYU. Number one, we own our buildings, or at least this building. We don't own all our buildings, so actually lease a lot of space, but we own this building and we expect to keep owning it for a long time. So maybe compared to other owners of real estate, like our willingness to look on a long long timeline is greater. We're not going to be selling in 5 years. So we can look out farther. And also because the student residents and you have 100% occupant turnover basically every year, we can actually take this building offline for a year while we do the renovation, right? So we're going to close it at the end of the spring semester. It'll be offline for a year and we'll bring it back online in the fall of 2024. So that's another advantage that would be trickier, not impossible, but definitely trickier in standard multifamily residential construction. And so I'll wind up by just talking about that economic case and how we got this to pencil in, because it's very expensive. Adding internal ductwork to a building is extremely expensive, right? Like the marginal cost of internal insulation, okay, fine. You're going to pay more for electric equipment than gas equipment still, right? But fine. But adding that ductwork was millions upon millions of dollars, super expensive. So how do we justify that, right? And I think a big part of that is getting off of the simple payback train, right? And this means both looking at non-energy benefits, which everyone is talking about, but some of which are difficult to quantify. And I'll say on that, at NYU, when we talk about economic return, we only look at non-energy benefits that can be brought back to a dollar value, reduced cost of maintenance, avoided local law 97 fines, right? These things have a dollar value I can put in them. I've completely sold NYU administration on the health benefits, right? I've been like, here's the data, and NYU spends $100 million a year on healthcare, and we're self-insured. That's all actual money we're paying for people's care. Like those aren't premiums, like those are payments, those are claims. Some of that's because of unhealthy air in buildings, right? So we can improve that. So when I told that to, like our CFO, she said, so you're saying if you spend this extra money on the project, I can take that much money out of HR's budget to pay for health claims next year. And I said, well, it's not exactly that. She said, okay, so we're not putting that in the bar chart, but it's okay to have on the side as like a nice benefit. It's like intangible. But maybe someday we'll be able to quantify that, and it'll go in. So this is what the sales pitch looks like, right? Look at the 30-year total cost of ownership. Over that 30 years, and I use 30 years because it's somewhere in the middle, right? Like the windows that we're taking out were put in 1968. So those are 50-plus-year-old windows. The building equipment might last 15 years, might last 30 years. Heat pumps might not last that long. Who knows? They're all still new. Let's look over a 30-year horizon. Look at all the first costs. Look at the energy costs and other savings over those 30 years. The avoided local law 97 cost. And I assumed that at some point we would have to electrify that building. That if we were going to meet our 2040 goal to be carbon neutral, we have to electrify, right? There's no way to keep burning fossil fuels in the building and be climate neutral. You could buy offsets. That's not where we want to start, is with offsets. Maybe we would end with offsets, but we're not going to start there. Let's try to actually make the buildings carbon neutral. And we could have done this a cheaper way that could have been 100% electric. But if we did not duct air to the rooms, we would not have been able to be certified LEED, which is our standard, and would not have been able to be certified Passive House, which I think is an extremely important reputational goal for NYU, to have that third-party endorsement of our plan. And this all goes back to the fact, to draw it back to the embodied carbon, NYU is currently extremely incented on operational carbon. We promised the mayor that we'd meet our carbon goals in the city. We promised Second Nature, which runs the carbon neutral claims, that will go carbon neutral. We do reporting, we do all these things, we measure it, we track it, local law 97, there's laws, everything, operational. We do look into the embodied carbon. We have done internal calculations. We've done scope 3 calculations. For this project, we had a calculator, but we're not incented in the same way to look at every screw and bolt and say, what's its embodied carbon? Because we haven't set those pledges. We're not being rewarded. There's not certifications. There's not laws. There's not the recognition. So these things all, I think, have to work together to get owners to be on part with that. But overall, we think this is going to be cheaper to do it this way than to do the business as usual model. So we think it's going to be good for NYU and also good for the world. And with that, I'm going to turn it over to Michael.
Great. Well, Cecil, you set a great stage here. So how did we actually do this, or how actually we're going to do this on Rubin Hall? Again, to some of the nuts and bolts here, set the stage in terms of what the exterior envelope of the building is. And again, this is just around the corner of 5th Avenue and 10th Street, 100-year-old building, Greenwich Village Landmark District. Exterior envelope, as it exists today, is about 20% window coverage. About 66% of the walls are solid columns or solid walls or columns embedded in that wall. Then about 14% of that is slab that's uninsulated and that we could not do anything about, actually. So the windows were a significant portion of the project, significant portion of our research, a lot of time spent on the windows. We were fortunate to have the photo on the left that was taken shortly after the building was constructed in 1926. It was very high resolution. That was a great resource for us. You can see the photo on the right, building as it exists today. Much of the historic fabric remains, except for the windows that Cecil indicated were replaced in the 1960s with single pane steel, not historically appropriate windows. So as we started to dig in, we knew these were going to be a challenge, but they got to be even more of a challenge as we learned more. Started to work with NYU Landmarks Preservation Commission to understand what the sort of different design parameters were going to feed into the selection of the window product and its design. Starting with the historic criteria, either driven by just being stewards of the building or by regulational law through Landmarks Preservation Commission. We had to address the operation of the windows. They were originally double hung, sliding windows. We had to address the materials of the windows, which were originally wood. You'll see that we replaced them with aluminum framed windows. Landmarks had say over the configuration of the windows to simulate that double hung, especially the offset glazing that would have occurred on the former double hung window and that geometry that we had to maintain. The details, the width of all the framing, the extrusions around it, the trim was all dictated by Landmarks as well. The glazing area, we had to closely match what was originally historically existing. We had a little bit of flexibility because we were high performance windows as defined by Landmarks. And then consistency, really replace a portion of the windows. You got to replace all of the windows in the building so it's a uniform presence. And then performance, contributing to Passive House, Local Law 97 conformance. And then as we got into the design of the mechanical systems, making the mechanical systems work and reducing those overall size of systems. So we had to look at air infiltration, which ultimately dictated the operation of the window, and its thermal performance that led to triple pane glazing. And the material and durability, this is a big building, 17 stories, had to be maintainable. NYU can't paint the outside of the windows every few years, which led us to aluminum framed windows. Layering on a few more criteria, accessibility, student residents, anybody in the building has to be able to open the windows, which dictated the levers location, the force that one would have to extrude, push on to open the windows, and its general operation. Although it doesn't really look at from the photos, these were very large, 6 feet by 6 feet, double hung windows. Those are very large windows when you start to get into some of these details. They've presented a number of challenges, trying to clean the windows from the inside to reduce operational costs, minimize rain infiltration for students who leave their windows open during a rainstorm, and then having removable insect screens as well. So with all that criteria, we had to explain that not only to ourselves and to NYU, but also to Landmarks Preservation Commission when they say, well, why didn't you think of this? We said, well, we just thought of that, but we couldn't do that. Establish this sort of flow chart of our decision-making process to Landmarks. And we also brainstormed about what are all the various window operations that could work, starting on the left with a hopper lower, something that could swing in on the bottom, We found that that's so heavy because of large window size that would not be compliant with accessibility requirements. And we said, well, how about a casement lower? The bottom half could swing in. Again, that's 6 feet wide, 3 feet tall. That was hundreds of pounds. Hardware could not work with that. And we said in-swing awning lower, swinging in. Again, issues with the weight of that, issues with not being able to reach outside to clean the upper sash, even difficult to clean that lower sash. Students leave the windows open, rain would be pouring in, screen issues as well. And we said, well, outswing awning lower. Again, cleanability issues, landmarks does not like the protruding windows from the facade. It sort of affects the overall historic look of the building. So these were all eliminated through this process of working through this. We eventually arrived at 3 different options, working with Wausau and Schuco. Working with Wausau, the 2 on the left, awning out on the bottom. We start to develop that, see how that could work, although it presented some challenges. And then in the middle, the sort of adding to that also a in-swing upper for cleanability. With both of those, we found adding all that hardware, all that extra framing, it started to get very fat, very chunky, and affect the thermal performance because there was just so much frame and less glass. Didn't look good, didn't perform well. So then on the right, Schuco, shout out to Brad Davis here from Schuco, who was an awesome partner on this. They were in the development of a full panel tilt turn window. So under normal operation would tilt in with the for maintenance. It could also swing in to be cleaned from the outside. They were working on how to articulate the glass to make that look like a double hung window. They'd been working on that for a double glazed solution. We worked with them to develop a triple glazed solution using that system. So you'll see here our sort of final solution for the windows. On the left, we were fortunate in the 1960s drawings. They had drawings of the former historic windows that existed that were a great baseline reference for us. In the middle, the elevation of our new window. And on the right, a section through that showing that offset glazing plane to mimic the historic look. Went to Landmark's public hearing after multiple meetings with Landmark's staff. And they said, we're not ready for this. We can't do this. We've done passive house windows, but they're all, wood frame, Brooklyn townhouse kind of things, aluminum framed window, Fifth Avenue location. We're concerned. And then they gave us some tips. They said, well, maybe you can add on some more trim, make it a little bit more articulated. We went back to the office, discussed, well, now we're adding like more aluminum, more stuff, more embodied carbon. Maybe we should, grandstand in front of Landmarks. This is ridiculous. I talked my partners out of that. I said, we just got to get this project through. Went back to a public meeting with the support of New York Passive House and AIA, which is rare to get a project-specific support, and got this finally approved. So you'll see here on the left, that 1926 photo. On the right, the building as it stands today, and then with our proposed windows on the right in this slide, you can see closely mimicking the configuration and look of the historic windows. So enough about windows, let's talk about the exterior wall. I'll start with this floor plan, and what this indicates is a very dense layout. We were keeping the majority of the interior walls in this renovation, focusing on the exterior envelope. But Rubin Hall is one of the most affordable student residences within NYU's portfolio. And the way they do that is having mostly triple rooms. And we were, counting inches in terms of being able to fit in all of the furniture into these rooms. So thickness of that exterior wall mattered and moved us away from doing things like mineral wool. And we had to look at other solutions for insulating that wall. We started to do some probes. What on paper is a brick facade with terracotta backup. Once you open up the wall, you realize 100 years of history. Maybe there's nothing behind that plaster. Maybe that plaster is gypsum board. Maybe there's newspaper stuffed in there. Who knows what's in there? You can't actually rely on what that whole assembly is. In addition, on the bottom, you see the slabs were typically concrete slabs with this sort of loose cinder fill that's common of buildings in this era. And you can see the existing detail really doesn't point to reduced air infiltration on the facade. So like, how would we deal with all of that? So we developed this system. You can see a lot of other things come into play in the exterior wall as well. Of course, the windows, fan coil units. We routed the mechanical piping alongside as well. We took that unstable plaster. We will laminate a glass face gypsum board sheathing onto the inside of that, tape all of the joints, tape the joints down to the slab to the ceiling. That will act as our air infiltration barrier. Use open cell, water blown, low global warming potential spray foam, both as a continuous surface and then in between the studs. A variable permeance membrane on the interior face of the studs, and then the gypsum board finish interior to that. You see a sort of zoom in detail of that, indicating the sort of taping at all these transitions and a number of different things coming together in that whole assembly. In addition, I'll talk, the support of the windows became a little bit complicated. We said, well, can we attach to that hollow terracotta block? Structural engineers said, well, we don't know what that is. We ended up supporting the windows from these steel studs on either side that sort of reach out to pick up the window and support it. And it's sort of independent largely of the exterior facade from a structural point of view. Some of the details here, again, showing, taping all those joints, attempting to, have continuous insulation through to the window plane as much as possible. We also, with our consultants, ran the WUFI analysis of this. During the probes, we took out a number of brick samples, understood that brick was wildly different in different portions of the wall and different portions of the building, different absorption factors. This analysis helped us understand the potential water content and directed us to that open cell insulation, which would allow a little bit more breathability of that wall and not blow the building apart by changing its thermal dynamics significantly from what it had seen over the previous 100 years. So onto the mechanical systems. As Cecil mentioned, fresh air distribution through DOAS units and very high efficiency energy recovery. Units were placed on the roof with ducts going through down to the building, and that was now a challenge. I'll show some slides on that shortly. Air-to-water heat pumps located on the roof as well that would feed up to fan coil units in each room. Those same heat pumps on the roof would also feed to water heat pumps in the cellar for domestic hot water. We quickly learned that the shaft area was very limited in the building, but we were able to work closely with our engineers to get that ductwork size down to fit in all of those existing shafts. No new shafts through this building, no new steel framing, no cutting out openings, very tight coordination that then started to have sort of ripple effects too. You move plumbing, you have to make bathrooms more compliant from an accessibility point of view, sort of layers upon layers of outfall from this, but we were able to get all the equipment in. So where do you put all that equipment on the roof? Historic existing building, fortunately not an architecturally significant or distinctive roof plane, but it has a lot of these steps, penthouse, bulkheads, things like that. So not a free space to put equipment wherever we wanted, in addition to landmarks not wanting the equipment to be too visible. Existing roof, as it's shown here, all the yellow equipment, very little, just exhaust fans, basically, water tower, a few other things that are coming off, and lots more equipment going back in that was defined by zoning, landmarks, structure, geometry, trying to hit those existing shafts, and even things like noise code in terms of affecting our neighbors and complying with all noise code for all the equipment on that roof. We built a mock-up, as is pretty typical, going through the landmarks process, demonstrated its minimal visibility, and this was a really not controversial portion of the project from a landmarks perspective, fortunately. A little bit about the resilience story as well. Added an emergency generator to the project. Understood like what systems could we put on that emergency generator, worked to get the DOAS fresh air system on that emergency power that could temper the space. So even in the most extreme weather, the building will be between 64 and 90 degrees. Even when, you know, it's 120 degrees outside or 0 degrees outside, we can maintain that comfortable temperature and folks can shelter in place during an extended power outage. So the embodied carbon story in this is largely to all the existing stuff that we're keeping, right? Like over 94% of that existing building, foundation, structure, concrete, steel is all remaining. We're very surgical in walls that we're removing and really keeping as much as we can. 100 years old, hopefully we'll stay that way for the next 100 years as well. But in the little bit of new product that we are putting in there, we had very sort of limited things that we could have input on, but it's insulation and then finishes like gypsum board and flooring were sort of the places that we could focus on. And that at FXCollaborative, we have a list of sort of go-to materials and materials that we avoid and using and tried to use the best possible materials from an interior health perspective and embodied carbon perspective. And through the LEED framework, we have over 40 materials with environmental declaration statements that will be in the project. And we're shooting for exemplary performance in that category with LEED. So lessons learned, there's a lot, far more than 6, but we started this project, I think 2018, 2019 with a feasibility study with NYU, looked at a number of different building typologies. That feasibility study gave us a sort of basic framework and starting point of where the targets would be for this project. Start early on everything, start doing those probes early, start budgeting early, measuring existing conditions early, purchasing early, everything as fast as you can. Sweating the details, that existing or that feasibility study, while it said, okay, triple pane windows, and maybe, we had a call with a vendor at that point, and the salesperson said, sure, we can do, triple pane, double hung looking windows. But it wasn't until we got into the engineering department and how much can that hinge support, where can that handle exactly be, that you could really understand what was actually feasible or not. Similar issues with the mechanical systems as well, really had to get into the details to understand the options and opportunities. Both LEED and Passive House were useful frameworks, certifications to talk about the project, and LEED and that requirement for fresh air pushed this project and made that a non-negotiable issue as we looked for cost-saving targets. Blower door tests. Rubin Hall is occupied year-round. Unfortunately, we have not done a blower door test of the existing buildings. Students and their stuff are always in there, and we worked hard to try to do that, and it was just not possible to do, so we're doing it immediately before construction in the spring. And of course, over the past year, 2 years of working on this project, like everything, costs have been volatile. I think every time we got a quote for windows, the global price of aluminum or glass went up 30%. As we backed ourselves into the corner with one heat pump option, and looked at other things, we found, well, maybe there's another heat pump, but it has a 100-week lead time. And we just can't tolerate that. And some of those mechanical costs also went up with each iteration of pricing as we developed the project. So, of course, this was done with the support of many people, NYU, Cecil, his group, and the facilities group in pushing this. All of my colleagues at FXCollaborative, especially Jenna Rimkus, who's here today, and Lizzie Himmel, who were key folks on the project. AKF, who was our mechanical engineer, Stephen Winter for Passive House Consulting, SGH Exterior Envelope, Silman for structural engineering, and BCA for landmarks support. So with that, we're looking to prepare this building for the next 100 years. We've softened up landmarks for all of you, so they're ready for this type of project. And as Cecil mentioned, hopefully this is an example for all of you to go out there and tackle that other 1 billion square feet of pre-war housing and be an inspiration to all of you. So thank you.